Satyajit Patil, and I am presenting this paper Fully Functional Suffix Trees and Optimal Text Searching in BWT-runs bounded space. The authors of this paper are Travis Gaggi, Gonzalo Navarro, and Nicola Preza. I'd like to thank Dr. Sharma Thankajan for giving me an opportunity to present this paper. This paper is quite large, which is why we'll be looking just at the first half of it. Moving on to the abstract, uh, we have a problem with indexing uh, texts, and especially indexing highly repetitive texts. We've got genomic data, we've got software repositories, we've got version text collections like Google Docs, which have repetitive data. And whenever you update them, you usually just update like 5%, 10% of it, not the entire document. And when the system fails to recognize this, there might be a lot of redundant data around. We need to deal with this for sure. And there have been other developments related to this. For example, the run length FM index, which is an advanced way of FM indexing. Uh, it does the work well when it comes to counting the patterns, but the issue is when it comes to locating positions, there is a big shortcoming. There's a lot of issues with locating positions. The solution is this paper tries to propose a method of extending the same RLFM index, but it tries to make sure that it does locate it does the locate computation within OFR space. Now, as we talked, there's a lot of data around, which is the data explosion problem. Uh, again, this data is not new data all the time. This is more repetitive data. Despite growth, unique data is not really there. It's more like a lot of repetitive data, redundant data, if you might say so. For example, when you talk about genome collections, when you talk about Wikipedia, when you talk about GitHub or Google Docs, you usually just update a little part of it instead of the entire document or the entire code. That usually happens very rarely when you entirely change 100% of the text that is there. So there's a challenge of efficiently handling these repetitive data sets, and uh, pattern matching needs to be much simpler with regards to time and storage. The motivation is to enhance the functionalities of version management systems, and more importantly, bioinformatics deals with genome analysis, genome sequencing, and previous methods involved using FM index for compressing this data and indexing this data. However, FM indexing is not uh, good when it comes to managing a lot of data. So, when the data volume is very high, the FM index scales accordingly. So, if the data volume is incredibly high, FM index also becomes incredibly cumbersome, and it does not generally look at the uniqueness, it just looks at the data volume, which is not something that we are interested in. There has been some work on this RLFM index, which is run length FM index. This was proposed by Makinen and his team. This does its work well while counting pattern occurrences, and the storage is also quite minimum. However, when you look at locating positions, this algorithm has its shortcomings. Uh, Apart from RLFM indexing, subsequent approaches there like using limpleziv and extensions of limpleziv, as well as smallest grammar size, smallest automation. However, these methods were also not really very helpful when it came to locating positions. Uh, What this paper looks forward to is improving the counting time. So, like RLFM, which was introduced before, this paper tries to improve it so that uh, counting time is improved to O of m star log of uh, sigma plus n by r to the base w, where sigma is the alphabet size, r is the run length of a specific BWT. We try to make sure that the space remains O of r. So these are the distinct number of runs in a BWT. More importantly, what this paper intends to do is optimize the locate time. So locate time, as we discussed, have had issues with the previous algorithms. Locate time is not something that has been really worked upon. So this paper tries to do it in O of log of n by r time to the base w, and it tries to make sure if the space is also checked within O of r. Further, again, this paper tries to uh, increase the space, but in the process, it tries to improve the timing of this. So, just apart from managing the space complexity, this paper also looks at how to enhance locate time. Uh, Delving deeper into what the contributions of this paper are, is optimal general setting and optimal packed setting. So, in a nutshell, the general setting is the most basic form of setting, where you are just focused on a specific part of it. For example, uh, you just focused on counting operation. So, general setting would uh, try to use as less space as it can and try to improve the timing of its counting. However, for other tasks, it might need a lot more time. Whereas when you look at packed setting stores a lot of, let's say, metadata. It tries to compress a lot of information. So naturally, a lot of space is required. Uh, this is better for locating, might not be specifically better for counting in all scenarios, but it might be. Moving on to the propositions of this paper extends the RLFM index. So, what this paper tries to achieve is time complexity of O of m plus occurrences, space complexity of O of r of sigma plus n by r. It tries to ignore the ahead. These are the things that you need to know when the Burrows-Wheeler transform, the suffix trees, suffix arrays. These are the basic things that we've covered previously. And FM indexing, as well as the updated form of FM indexing, that is the run length FM indexing, are also important concepts which will help us navigate through this paper. Moving on to what RLFM indexing is. So, FM indexing has issues with repetitions. So, when you come across a lot of uh, BWTs where you'll see a lot of characters occurring all together. So for example, you'll see AA, BB, BB, BA. So B occurs all together for a long time. So what RLFM does, it tries to manage these identical characters more efficiently than FM indexing does. So it uses something called run length encoding. So when you have like AAA, BBBB, AA as your string that is to be worked on, what it does, it captures the first occurrence of each run. So for AAA, it will just keep tabs on the first A, and then it notes down that there are two more A's after that, and then it does the same for B, and then again if A occurs, it checks for that as well. So to perform efficient operations, what the RLFM does, it uses a data structure which is called as a predecessor data structure instead of a bit vector which was used in RLFM. We'll be exploring more of this as we move ahead. So, the important concepts in RLFM indexing, the LF mapping. So, LF mapping allows us to map positions in the BWT to the positions in the suffix array, and the equation is the suffix array of LF of the pth position is equal to the suffix array of p minus 1. Uh, Now, the more important part of this is the efficient rank calculations. So a rank function is important. What a rank function does, it counts occurrences of a specific um, character up to that point. So if you want to find out uh, the rank, the number of times that a specific character, for example s, occurs in a specific sequence, what it would do is it will look up the string, and it would look up the position which we are interested in. So if we want this rank of s in the seventh position in a given string, for example SBSSCB, so as soon as you reach the seventh position, you'll notice that you have three occurrences of S up to the seventh position. So there you have your rank S is equal to 3. So what RLFM index does is it tries to use something called partial rank operations on the run length encoded structure, which improves efficiency instead of using an entire rank operation on the entire string. So, while locating occurrences, we have three lemmas that are very important when we look at the entire picture of this paper, or at least this section of this paper. So, the lemma 2 works on enhancing the backward search process. So, in FM indexing, you have something called backward search for Burroughs Wheeler transforms, which checks the previous element. So the enhancement is done in such a way that we at least get to know one position during this search. Uh, Again, we have more additions to this. We have got the lemma 3, which provides a method to find the neighboring cell. So as soon as we found one element in a specific range, uh, we will find it more easier to find its neighbors. So if we want to query out the element that occurs before it or the element that occurs just after it, lemma 3 takes care of how to efficiently get that and provides solutions accordingly. Um, the third important lemma is the lemma 4, which uh, does the same thing as the lemma 3 does, except it uh, uses additional space, and it um, uh, enhances the locating process by um, you know extending the range of what lemma 3 uses. I'm going to look at all the lemmas one by one. Moving on to lemma 2, we are going to see what lemma 2 does. So what it introduces is sampled characters. So let's say there are specific characters in a BWT that matter more than the others. We're going to delve deeper into this as later on, but for now, just let's consider that there are few characters in the BWT that mean more than the others in the overall context. And we introduce a new structure called RC. So RC is something that stores all the different occurrences of different samples uh, in our BWT. When it when we pair it with the suffix array of the position p and -1, it gives us the text position of this character in t. Again, what we also do is we find the suffix array interval. We use the RLFM index and backward search to find the interval SA of SP and EP, which is the start point and the end point, where all the suffixes which start with P are located in the text that we have. So during this process, we get at least one occurrence of P in T, considering that uh, P occurs in T. So, I mean, if it does, uh, we find at least one occurrence of this P in T uh, in the given interval, starting point and the end point. Um, Further ahead, what we do is we conduct efficient backward search with the predecessor structures. So for each character P of jth index in the pattern P, we use LF mapping to find the previous character in the BWT, which gives us the preceding character in the suffix array. If we encounter a sample character in the BWT which matches this jth index element in our pattern P, the predecessor query can give us the required position of that specific P in the suffix array. The time complexity of this is O of log of n into sigma uh, divided by r, and this log is to the base of w, where r is the number of runs and sigma is our alphabet size in the text. So, like I said, sampling is something that we are going to look at in more detail, and here it is. So, we say a specific character is sampled if the character preceding the position of the first suffix in the suffix array, or if BWT of P is not equal to BWT of P minus 1, then we know that there is a change in occurrences of a specific element. So, for example, we've got A, B, 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 and A again. So, we know when A is not equal to B, which is BWT of P is not equal to BWT of P minus 1, is when we know that B has occurred and not A when we were expecting A. So, that means that B at when we encounter B, we use B as a sample position, and then as we move ahead, we find out more B's. Then in that case, we won't do anything until we find a distinct element from our given run. So, in case you didn't understand what I mean, what I meant in the previous slide, we're just going to go through a small example. So let banana be a string, and a BWT, a Burrows-Wheeler transform, would be ANN, B, $, A and A. So BWT of P at P is equal to 1 would be A. P minus 1 obviously does not exist. So in this case, we can say that BWT of P is equal to BWT of P minus 1. Then that's not true. So what we do is, do we consider that to be a sample element? Yes, we do. Similarly, for N, and the previous element in the BWT is A, we again check for this condition. What we find is no. So we consider that to be a sample element. Now at this point, we are seeing that n is equal to n. So this condition is satisfied. So we see a repetition of elements. So is it a sampled element? then the answer would be no. So you must be uh, starting to see a pattern here, that when we encounter two same elements, we don't consider them to be a sample element. But when there's a new element that occurs, so for example, B is there and the previous element is N, we find that this element is new. So a different run is started for it and a sample element is inserted here. Moving ahead, we are also going to see what the RC structure that I mentioned in the previous slide means. So we have all sample characters here. So in the previous slide, we have all the yeses, which signify our sampled elements. So we've got p is equal to 1, p is equal to 2, p is equal to 4, p is equal to 5, and p is equal to 6. So these are our sampled elements. So what we do is we store information in these. So for every single element, so for example, we have got A. So for A, we store position wise information. So P is equal to A will have um, related information with P is equal to 1 and P is equal to 6. Similarly, for N, it would have just 1, B would also have just 1, dollar would also have just 1. We're going to see more in depth in the next slide. So for character C is equal to A, we see it occurs at two distinct positions, which is P is equal to 1 and P is equal to 6. So it finds out the occurrences of P is equal to 1. So T of the suffix array at this position P is equal to 1, and that becomes 5. So when T of 5 minus 1 is T is equal to 4, which is A. And so what we do is we get our RA and we store 1 as the first index and first key, first value of the pair, and 4 as the second value in the pair. Similarly, for P is equal to 6, we find out the corresponding the number of interest is 1, so we get 6 and 1 in that case. So we have our RA, which is 1 4 as one pair and 6 1 as another pair. Similarly, we follow the same operation for C is equal to N, where we find P is equal to 2 and then the corresponding index in within T is also 2, so 2 and 2. Similarly, for B we find 4 0 and for C we find 5 3. So looking at the bigger picture here, now we're just going to see how pattern matching occurs. So let's say P is equal to A and A is our pattern and T is our main string. So we first start with the first character from behind, which is the last character, which is A, and we conduct a backward search on it. We use the RLFM index to find the interval where A appears. So suppose this appears within these two indices, which is 0 and 2. So we locate at least one occurrence of it. So using the predecessor structures RA, like we saw in this slide here, we find a position P in this range that corresponds to a sample character in the suffix array. So just as an example, if we find out that rp is equal to 1 and then from our data structure we find out that the suffix array of 1 is equal to 5. So if 1 and 4 in this instance, if it would have been 5, then we would have concluded that there is an occurrence of A at position 5 in our main text. Moving ahead, once we successfully get our successfully get our answers to A, we get back to the second last element, which is n. We conduct the same exact procedure for n, and uh, if that succeeds, then we also go for a and a, and then we find at least one such occurrence of this pattern a and a and this string. uh, we compute the intervals, the start points and end points covering all occurrences of p is equal to a and a eventually. The stored position p gives us at least one confirmed position, and we can extend this function to find out all positions in this text, and especially in this suffix array from start point to the end point. And this is done, and the propositions in the looked at lemma 2. We'll also be discovering what lemma 3 does, but before we do that, we have to go through a couple of terminologies. So the first terminology would be, uh, given a permutation phi. Uh, this phi tells us how we can store or calculate the preceding and the succeeding suffix array position for a given text in position t. So if we know that the suffix array position p of we can get the phi I, which gives us the preceding suffix array position. If the inverse suffix array of I is greater than 1, then phi of I is the suffix array of the inverse suffix array minus 1. This moves backward in the suffix array. Otherwise, if phi of I is equal to SA of n, this moves forward with the suffix array. So just like we've got the phi, which gives us the previous element, we've got phi inverse, which gives us the succeeding suffix array element for a given element at position p. So for example, we've got our example banana from before. So the suffix array would be this, and the inverse suffix array would be this. So for example, if we consider I is equal to 4, like we used I here, so ISA of ISA of 4 would be 3. So the inverse suffix array at index 4 is 3. Yes, we found 3. So phi of 4 would be SA of this 3 minus 1. So all the occurrences before that. So SA of 3 minus 1 would be SA of 2, which is 4. So phi of 4 would be 4. Similarly, for the inverse phi, we've got the succeeding position. So for SA of 4 plus 1 is 5. So at position of 5 in the suffix array, we've got 0. So that is our inverse suffix array. So this means that the preceding suffix array for position for A is at index 4, and the succeeding one is at index 0. So this is what phi and the phi inverse helps us do. Furthermore, we are going to see at something called a phrase. A phrase is a small chunk of t or a small substring of t which starts with a sample character. So for example, we've got P as a starting character, we've got A as one of our starting characters at position 3, we've got N as a starting character at position 5. So we essentially split the main string into these different parts, so 1, 2 and 3. So these 3 are our phrases, and all of them start with a specific character, and that character has to be a sampled character. If you remember from what we'd seen before, the sample character is something which kickstarts a specific run. Um, Now, once we've seen the definitions, we'll move to the lemma 3. So, lemma 3 looks at the so if we have SA of a specific position P, the lemma 3 looks at what the preceding suffix array element is and what the suffix succeeding one is. So we need more data structures for this for sure. So we use a predecessor data structure which is P plus minus, and store an O of R space predecessor data structure, which is a type of data structure which allows better querying for the previous and the next element. We also use another data structure which is called the next positions data structure. The next doesn't necessarily mean the succeeding one but also the previous one. So n of I would be SA of q minus 1 and SA of q plus 1 if we have SA of q as the suffix array element for a position at I. So n of I is corresponding to SA of q. So it gets the previous element, it gets the subsequent element. So what lemma 3 deals with with is it finds the starting phrase position. So it finds the first phrase, then it it does this through querying the predecessor data structure. It tells us where the first character of the phrase is, and then it uses n of I to retrieve the suffix array position. So it gets the previous and it gets the subsequent element after starting phrase for position. So let's see a short example. Again, we get our full text, which is banana again. Um, let's assume that our sample positions are 0, 1, 3, and 5, which are indices in T where the phrases start. So where sampled elements begin and sample elements kickstart our phrases. For each sample position I in the data structure that we've created, we store n of I, which give us the previous and the following element in the suffix array for that specific position. So firstly, we locate the sample phrase position. We identify the T0. T of 0 is a part of the phrase starting at index I is equal to 0 in the data structure that we store. We retrieve our neighboring positions. So from our pre-computed positions, n0 is 6 and 5. So like we had seen here, we get those elements from this data structure, and once we do that, we find the SA of p minus 1, which is SA of 3, which gets us 3 and 5. Similarly, for SA of 4 is equal to 0, the preceding position is this, and the succeeding position is this. So SA of p minus 1 and SA of p plus 1 are efficiently stored, so we can retrieve these values in constant time. Once we've seen lemma 3, lemma 4 becomes clearer. So this lemma states that we can store a data structure of O of RS words such that given a position SA, we can get the suffix array position P minus J and P plus J. So instead of just looking at the previous and succeeding elements, we take steps of J. So the element that was at the position J prior to P, and the position J which is ahead of P. So we extend lemma 3 and we call it lemma 4. So the way this happens is we divide the BWT positions. We identify certain positions in our BWT that give us the starting positions These are called S sampled. So we pre-compute uh, position ranges. So we construct two arrays so that we can look up faster. So p plus and p minus. So just like what n of I did with s of p minus 1 and s of p plus 1, we do a similar operation, but the scale is a little higher this time around. We map the BWT to the text positions, and we look towards efficient querying to answer queries for SA of p plus j. We find the nearest sample position in p plus and p minus, and then we calculate the suffix array that is in question using this reference. So this works in both non-unary and unary ranges. So the unary ranges are where the characters are the same. So for example, we've got a b b b b. So it correctly checks for unary ranges where b is our subject, and ahead of it is also b, and behind it is also b. And non-unary is the position where we find our borders. So where a and b are the previous and the subsequent element. So all in all, this lemma works in both the cases, and it helps us to calculate our suffix array values much more. Moving towards the main part of the paper, we're going to look at how counting and locating is done. So we're at the common point of both, where the first process is chunking the text. So the text is divided into s different chunks. So each chunk is of n by s size, and the original text is padded up with the symbol dollar if necessary. So as all the chunks have been created, a new text t star is created by concatenating all the chunks, and the length of t star for reference is n star. Suffix mapping is one concept which is important to what we'll see ahead. So a suffix in t star corresponds to a suffix in t from where it was extracted. So we have to see parallels between our transformed text and our original text. So the first one is the suffix mapping. So we have two more lemmas which tell us more about what we've seen before. So the first lemma, the sixth lemma, is the lexicographical order of the suffixes is preserved between t and its transformed version t star. So this lemma essentially tells us that t star from I to n is lower than t star of j to n, um, and that is if the original string also exhibits the uh, same property. So if the original string has t of I to n of a lower lexicographical value to t of j to n, then the case will be similar with t star of I star to n star, and t star of j star to n star. What Why this property is important is that it allows us to draw parallels between the main string and the transformed version and these parallels can help us draw inferences for various algorithms. So essentially we can use this transformed t star for different operations, for like ranging or searching, and since this t star is much more efficient than the main original string, we can help narrow down a lot of time or space complexities that we would have encountered if we used the original string. The next lemma is the lemma 7. It tells us if the Burrows-Wheeler transform of a string has r number of runs, then the BWT of the transformed string will at most have r star runs, and r star is equal to O of r into s. So s is the number of distinct meta symbols that have been used in our transformation T star. So these two lemmas will be important as we move ahead. One more important point here is mapping the alphabet. So we've created a new text which is T star, and the alphabet size is denoted by sigma s, sigma subscript s. What this tells us is the number of distinct characters that are in the transform string. Uh, we can by intuition figure out that this alphabet size can be incredibly huge, because this string is chunked, it has more meta symbols in it, and then it's grouped again together, it is merged together again, which means that this alphabet size can be very large. However, it has been pointed out that the effective alphabet size is bounded by O of r into s. And although this might not be very uh, low, this is much smaller than n star log n that we previously had, ensuring that this alphabet size is still manageable and we can move ahead with it. Furthermore, to efficiently handle the transformation and the large number of meta symbols in our alphabet, the algorithm uses something called a trie, and a trie is a specific form of a tree which efficiently handles storage and retrievals, and a compact trie is used for our uses. So the trie in turn uses something called perfect hashing to efficiently to quickly find a specific node which corresponds to a substring, which makes the operations efficient and ensures that every single operation can be done in very less time, and in this case it can be done in constant time. A try uh, with the help of hashing uh, can just insert a key value and a key, and it can retrieve a value. So this can be done in a constant time. So with regards to storage, the substrings of length s from the original string t are stored in a separate memory to the transform string. One more thing is a new term which is called primary substring, which refers to the substrings within range I to j, which consist of at least one sampled character. So the sample character that we had introduced in the second lemma comes back into picture here. Uh, why we care about these primary substrings is because they let us know about the parts of the string that are used for transformations or indexing. That is the significance of. So now let's move to counting in optimal time. So like we've seen previously, we'll create a transform string t star from t, and we'll process the fm index of t star. So like we've seen, the fm index has its own data structures. For example, c of this smaller c tells us the number of times meta symbols smaller than c occur in that uh, transformed string t star. And L star would similarly give us the BWT, So L denotes BWT, and L star would denote the PWT of the T star. Um, One more thing we look at here is the pattern transformation. So, so the transformation of uh, the pattern is as important as the transformation of the text itself. So the main aim is to, you know, transform the pattern such that it uh, has the same meta symbols that uh, T has. The pattern P is broken into different parts and then extended using padding. So LP and RP are two um, additional patterns that are used to pad P, and LP is used with the smallest alphabet symbol, and RP is used with the largest alphabet symbol. You might now ask yourself why LP and RP is used. So the reason for this is, you know, if we don't use LP and RP, we might miss some partial matches at the boundaries, and we don't want that. And LP and RP is something that can help at either ends, either with the smallest symbols or the largest alphabet symbols. Uh, they also simplify, matching at the edges. So edges or the boundaries. The main part of using LP and RP is to make sure that matching at the boundaries is done in a more efficient and in a more exacting manner. Also, it helps with reducing complexity in matching without repetitions. So instead of keeping on trying to match the text with the pattern, LP and RP would rather help it lower down the number of such comparisons. Now, for mapping these patterns, the algorithm uses a compact trie. So, like we've seen previously, the compact trie is used in this process as well. The trie, it essentially maps the symbols of p star into numbers from 1 to sigma star. So sigma is something that signifies the alphabet size. So if a meta symbol of p star is not found in the trie, this means that uh, the non-transform, that is the original pattern p itself, does not occur in t. So for LP and RP, the trie is used to find the positions in T star that denote the patterns alphabetically ordered bounds. So while doing this, the algorithm actually at the start uses the standard FM index and not the RLFM to handle the first part of the backward search on LP and RP. However, it later on switches to the RLFM index for the remainder of the search. According to the authors, this switch is something that optimizes the search, and this is what they found to make their queries more efficient for larger text. Now that we've seen how counting in optimal time works, we'll also look at how locating in optimal time works. So, if you remember what we've seen in the first slides while discussing what the gist of this paper was, we were more concerned with locating in optimal time because this is something that a lot of papers did not mention, but this paper tries to do this. So, toe hold technique is something that we've seen in the second lemma. This is used to efficiently locate the ranges of the suffixes in our SA corresponding to a specific pattern in string. It uses a try and a suffix array. So a try is used to map the symbols of the pattern of in the suffix array of this of the transformed suffix array. There is, however, a change in this process. So when the patterns are searched, the LP and the RP are searched, the algorithms needs to change itself accordingly. So when the pattern is broken down into segments and processed, each segment uh, corresponds to a node in the try. So at each internal node in the try, we reach by p of m by s into s plus m plus 1 all the way to m. The suffix array of p p should be stored in the suffix array, the transform suffix array. Why does this help? Is this helps the algorithm to link the current segment to its corresponding position in the suffix array. Once the try node is successful in storing the suffix array at position p, the algorithm can continue using the same approach that was used in the lemma 2. Uh, so now, when it comes to locating the pattern in the text, uh, what we do is we get an interval. So, like I said previously, we follow the lemma 2. We recover the starting point and the ending point of the transform suffix array. Once this is done using lemma 2, the reverse is also possible. So in the transfer, if this works on the transformed suffix array, we can infer that this works on the original suffix array as well. So the algorithms can convert these positions that has have been found out to their corresponding positions in the suffix array of the original string, and this is denoted as SA. So once you have this position SA of P in SA, you can easily map it back to SA of P, since the transformation of T to T star is structured, and this step can show that mapping can be done more efficiently. Um, so I think we've covered the main part of this paper. So here the conclusions are, so mainly the occurrences of the pattern in a text with alphabet size and given number of runs can be counted in uh, O of m into log of sigma plus n by r time to the base w. The main part is the location. The locate operation can be done in O of occurrence into log of n by r to the base w, as well as we can use an index with O of r space. The main part of this is the optimal space and time. So we can see these terms denoting the space that have been used. So if the space is increased, the counting time can be improved. So there's a trade-off to look forward at that point. In the packed setting, we generally require a larger number of space, and the counting time can be lowered because of this packed setting. So, like in the initial slides, we discussed how packed settings work when compared to the general settings. General settings do not have additional functionalities, they work towards a singular problem statement. Packed settings, however, can compress themselves and can store additional data. We can call them something synonymous with metadata, but even though they use more space, they can help us in locating and counting times in a more optimal way. This study can also tell us more about the number of BWT runs, which tells us in turn about the compressibility of repetitive text. It tells us that BWT runs can efficiently handle compression of highly repetitive texts. Uh, this method also, outperforms earlier space-efficient alternatives by a large magnitude. So the authors say that this is one or two orders of magnitude, and this is specifically while locating. So I think the authors have really thought about locating and not just counting, which the other works seemingly have. So one more thing to point out is the impact that this study has had on further research. So there's something called RLCFG, which studies on string attractors, which has been developed after this. And the scope is even higher uh, when you introduce new bounds on text compressibility and the creation of multiple data structures, and working with strings or texts in more depth. I'd like to thank you for